Mhm. So now, like okay, you conduct a three-arm clinical trial to assess the effect of new drug X on systolic blood pressure among adults in Freetown, and compare the systolic blood pressure after 12 weeks of using the drug. So we want to like compare new drug X, which is the new drug, to the active like comparator of old drug Y and placebo. So previously, maybe people in that Freetown have been using old drug Y and placebo previously. So the inventor of like new drug X wants to check like the effectiveness, if it's really effective compared to the two drugs, or it just behaves similarly, like this same way as the two drugs, like the old drugs and maybe the placebo. So that's what this trial is all about. So we are going to use our BP trial. Actually, we're going to use our BP trial data. We start by like loading the data first, using the read CSV. You specify the data.csv to like load the data. You might be interested in seeing the first 3D observation actually. So as you can see, okay, let's open it from this view. You can see we have the systolic blood pressure, we have the treatment, and we have the treatment coding actually, which 0 is placebo. Let's go down to see what happened again. We still have placebo, 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 placebo. Still have placebo. I'm coming. Let me just drag this down a bit. So you can see old drug Y is 1. Old drug Y is 1. And new drug X is 2. So we have 3 groups. We have the placebo, the old drug Y, and the new drug X. So now you might be very interested, like you might want to create, what are they calling you? You want to create a summary statistics to check the median, the mean, 75 percentile, 25 percentile, and so on, the maximum value for each groups, and so on like that, to have like a quick summary of the groups. So, and you might want to like, it's not that you might, it makes sense if you like draw a kind of box plot to see the behavior of how the drugs behave, how the treatment arms behaves. So you might want to see that. So as you can see from this, from a quick view, you can see that placebo tends to have like higher systolic pressure, systolic blood pressure, than compared to the two groups. And new drug X tends to have like a very lower one, like systolic blood pressure. So what we want to see, that is the treatment, is it actually significant? So that's what we want to see. Like, are they really different from each other? Are they different from each other? So you want to like confirm the assumption, like what I call it. You want to confirm the assumption of normality. If the data is normally distributed, if it's not normally distributed, is it greater than 30? You want to confirm that. So that is the first thing we have to do, checking the assumption of the data we've generated so far. So how do you check the assumption of normality? Like, you have to like plot a kind of, you can plot a histogram, yeah, or density plot. That will give you if it's normality. Sometimes box plot, if you plus a box plot like that is sleeping not standing, you might see if the data is normally distributed. And there are some other statistical tests that might give you like just some coefficient to determine if the data is normally distributed or not. So now, as you can see, this is the histogram of the systolic blood pressure. So if you look at this, yeah, it's looking like a normally distributed solve, because this histogram like illustrates a bell shape. This illustrated a bell shape, which we can say that looking at this, it's like it's looking like it's normally distributed. So there is a test, like I'm going to like talk about sharp we call it is it Sharp-Ro? Yeah, Sharp-Ro test actually. So if you have Sharp-Ro tests, you can just specify your data and the variables. So it's going to give you like, it's going to like tells you if this is normally distributed. Looking at this histogram, this histogram shows that it's slightly normally distributed, but this test is saying otherwise, that no, this is not normally distributed. Yeah, this is not normally distributed. This test is saying otherwise, actually. But let's see the number of samples we have to know if coming dimension of, yeah, BP trial, the trial. Yeah. So we have 900 observations. So we have 900 observations. And if you have 900 observation, if you see maybe we have 900, I'm coming divided by 3, right? Let's see. So if you have like 300 per observation, that is like extremely greater than 30. So that forms like our intuition to say that, oh no, we can go on with the assumption, because each are like this sample size is greater than 30. So that's why we are making that decision that, oh, we can still use ANOVA. That's assumption one. We've confirmed the normal distribution, where the normal distribution, if it's normally distributed or not. So, and we validated that because the sample size is greater than 30. Because looking at these, like looking at these histograms, it looks approximately normal. But looking at its test statistics, like that is like outside the scope of this class, it shows that it's not normal. It's like slightly different and differentiated from normal distribution. So now we want to like see the next assumption is like the standard deviation, are they approximately like equal, because the standard deviation must be approximately equal. So let's see what's so we have standard deviation of 21 over here. So we have standard deviation of 20 and 20. So this standard deviation are approximately equal. So then we can still use what? We can still use ANOVA. So, and the third one is that are the samples drawn independently? That is, the group in the 3 arms, like the individual in 3 arms, are they like drawn, like are they drawn from the population independently? So, and we know that in a randomized control trial, normally like it's random. So, and anything that is random is drawn independently. So it's drawn independently. So we did assumption of independency, sample size being independently drawn is odds. It odds. So now we can go on to like implement ANOVA. So we try to like write ANOVA into objects. If whenever you want to do ANOVA test, it takes this function called ANOVA, and it takes formula. It's just like the same formula like we have been using in independent sample test. It takes the data, the variable with the data. Like let me just say variable, takes variable with the data, and with this approximation sign, with the variable with the labels. So the labeling variable. So, and it's going to take your data equals your data. So this is like the formula we use to like to, let me just comment this out. Yeah. So this is the formula I use. It takes the variables, the variable with the data, the actual data. Like when I mean the data, maybe the what you are measuring, which what you are measuring in this case is systolic blood pressure, with approximation sign against the labeling variable. So now we write this into good morning. You know, we just save it like into good morning. You can save it as ANOVA 1, ANOVA 2, as you like, as it pleases you. So once you
So I have
summarize,
a question, Daniel. It's a you can keep sharing your screen. Yeah.
okay.
So it's about the variable. So instead of using that tiled sign, which is your approximation sign, I think they call it tiled or
Cool,
tilde.
title. Thanks for that.
Yeah. So why not use the dollar sign to like reference it? So do you know the data analysis? So it's BP trial dollar sign SPB, comma BP trial dollar sign treatment. So use the dollar sign to reference the so these are the column names
Yeah.
instead of using this tilde sign. I don't know. I'm just
Yeah. Okay.
that's
Okay.
what I always see. Yeah.
Let's try something. Coming.
Okay.
Let's try something. Let's see. One. Okay. Let's see what it gives us. BP trial, and this, right?
Yes.
Okay, comma BP trial, and this, right?
Yeah, then the name of the data, so comma data equals BP trial.
Data equals BP trial. So can you see we're having error, right?
Okay.
Yeah, because for every function takes certain set of arguments. So, and the way the arguments are being like the kind of argument it takes, like depends on how you are going to fit your variables. So this in this context, this has been working for what are they calling it? It works for I think is the paired sample test, right? I think this worked for paired sample test, and I think it worked for independent sample test too as well. I think so. I think it works for independent sample test too as well. So you cannot use comma in this context. So you have to use the type sign.
Okay.
Yeah. So
okay, thank you.
Yeah. So once you just know like the formula you are taking is like it takes the variable with the values, the variable with the values tied with the variables with the label. That's just what you have to just know. So once you summarize this, we are going to have the degree of freedom. Degree of freedom. There is a way they calculate this degree of freedom. We are going to have the sum of square treatment and the sum of square residual. We are going to have your mean square error and mean square treatment and mean square residual. We are going to have the F statistics because this is this is three groups. This is ANOVA. It's like comparing means between three groups, right? Three or more groups. So it's changes from like a T statistics to F statistics. So that's why we're having an F value and we're having the equivalent, the associated P value. So now we need to like formulate our hypothesis. Our hypothesis is that there is no significant difference between the means across the three groups. That is across the new drug Y, new drug X, old drug Y, and placebo. And our alternative say that there is significant difference between the means across the groups. So that's what it does. So can someone please just like unmute and like try to like interpret this for us based on this p-value? Anybody?
There is a significant difference between the groups.
Okay. So comparing it to 0.05, there's significant difference between the groups. So yeah. So now another question we want to check is that when we're talking about two-tailed test, right? It tells us the significance different, right? But we want to know like which groups differs from another. Like we might want to know, is it from there is significant difference between the new drug and the old drug, new drug and the placebo and all this kind of stuff like that. That's where, because this is the three groups, so there is a test called Boniferroni. That's what we use like to check if there is significance, like the significance between different groups. So this is not like doing like a one direction, two direction and seeing like doing upper greater test or lesser than test to know which one is greater than, which one is good, which one is not good, and all this kind of stuff. So we use Boniferroni correction. So now it's called like, it's like a pairwise test. Yeah, pairwise test. So that's what most people call it. So it takes the argument of pairwise test. So it takes X. So the X is the variables with the data. No, don't say the data. The variables with the with the what you measured, which is systolic blood pressure in this case. And this, it takes G, which is the group, like the groups to the variable. Then the P dot adjusted method, yeah, should be set to Boniferroni. So I don't know if I have to go over that again. This is a pairwise test. A pairwise test. So it takes group, it takes X, which the X is the variables with the data. It takes the labeling or the grouping groups, which like associate, which like give the difference between this one, because this is the labeling group actually, and it takes p dot adjusted method to be Boniferoni. So once you run this, you are going to see something like this. So you can now see it's just like in a matrix plot. So it's comparing each group with each other. So you can see this heading here, you have drug new drug X, right? You have old drug Y. At this Y axis, you have old drug Y, and you have placebo, right? If you check between old drug and new drug, you are going to see that this is actually lesser than 0.05. So there's a significant difference between this new drug and old drug. So once you check placebo and new drug, like you check placebo and new drug, you're going to see that there is significant difference too as well. So once you check placebo and old drug, you are going to see that there is significant difference. So that's how you know like which groups differ from another. If there is no significant difference, you are going to see like the p-value greater than 0.005. So if you are comparing with 0.05 or 0. It's going to be greater than the p-value. So that's how to compare and see which group differs from which group. So I think that's all for this, for this lab 3. So is there any question before we move to lab 4? So any question before we move to lab 4?
Can you please share lab 4?
Okay, thank you. So so now we'll be talking about correlation. So correlation, I know. Please, can someone just like I know maybe you've done this in the main class, because this is just like a lab sections. Can someone just like omit and tell us what correlation is? Anybody?
I think it's relationship to show how maybe two variables are related. For example, maybe smoking and lung cancer. You want to show like the correlation between that kind of a thing, where if there's a strong correlation between smoking and lung cancer, or maybe if it's a weak correlation, so something like that.
Okay, thank you very much. So so correlation assess the extent to which two variables are related, like what happened between two variables X and Y. If X increases, does Y increases? If X decreases, does Y decreases? If X increases, does Y decreases? Like looking at what happened between two variables, two continuous variables actually. So that's what correlation does. Is it continuous? Let's just say two variables, but I think it's two continuous variables. So we're making use of this data, but I found out that I think I need to like raise an observation. So for this correlation, because this data, I don't know what's happening to this data. I've tried to like load. I don't, even in the shared documents, I don't seem to like see this data, but we just like use maybe the data we have been using before to find the correlation between two or more groups. So let me just comment this out. Yep, let me comment this out. So we have this data called resident doctors. I think we can use that for this case. Ideally, we should use that data, but I don't know what's happening to that data. I've tried downloading it. It's giving a whole lot of errors. I want to look for the resident data so that we can make use of that. Okay, just copy this. Resident doctors. Okay, just from here. So now let's see what we have in the resident doctors. Yep. Okay, now the resident doctor now. So maybe we want to check what happened to the mental health score with respect to job satisfaction. So, or what happens to okay, let's check the age and the job satisfaction. Actually, the age and the age and the mental health score. We want to see like the relationship between the age and the mental health score. So what correlation does is that it helps us assess to what extent or what happened, like the relationship between two variables. Yeah, two variables. So now it uses like the what are they calling it? You can plot your before like doing the correlation coefficients, you can try to like make a plot for that. For me, let's try to make a plot by using ggplot2. So you need to like force library. You don't even really need ggplot2. You can just do plot RDS, then you check age, RDS, then you check mental health score. So you can see the way the this looks like. You can see the plot. So we can see this is mental health score and this is age. So you can, from this you can slightly say that, oh, there is like slightly positive relationship, because you can see that not really the relationship might be very weak because it depends on the direction of the point, like, and how the point are very clustered in a particular region. That's like determine the relationship. But as you can see that some of these points, like if you want to like fit a line, you are possibly want to like fit a straight line. So these points, some are going up, some are spreading like this, like that. So when you have like a very strong positive relationship, you are going to see that almost all the line are in straight line, like moving upward. That's like positive relationship. When you have like a negative relationship, like they move from like this upper region to this downward region, like they move this direction. So they move this direction. So when there is positive relationship between let me just say, okay, assuming there is positive relationship between mental health score and age. So that tells you that as the age increases, mental health scores also increases. But when there is like negative relationship between mental health scores and age, it tells you that as the age increases, mental health scores reduces. As mental health scores increases, the age, maybe the age of the person is very small. It doesn't increase. So that's what correlation tells you. So now let's go to the actual okay, we use the function called COR to like do the correlation to carry out correlation analysis actually. So now we are using our mental health our resident doctor data, right? So RDS age as the x, comma, it takes argument x and y, RDS $sign mental health score. Let me comment this out and bring it up. Yep. So once you do this, so you're going to see that there is like a very weak negative relationship between the age and the mental health score. There is a very weak correlation between them. Very weak correlation. So now we have different kind of correlation method. We have the Spearman, we have the Pearson's correlation, and we have the is it Kandau tau, like that. So you might be interested in like specifying the method you want to use. Maybe I want to use Pearson's. Let's see, Pearson's coming. I think it's take C. Yep. And then it takes, yeah. So, oh, okay. Yeah. So if you use Pearson's man, sometimes there may be like slight difference between those correlation method. So and I think Pearson's is used for like a population kind of stuff, while Spearman for a parametric kind of parametric type kind of data that follows normal distribution, and Spearman is used for like when you have these non-parametric data, like let me say the data are not normally distributed, the center of measure of central tendency uses the median. I said this Spearman is ideally so, but most time if you use them simultaneously, you are going to have like very close what are you calling it? Very close coefficients. Spearman. Yep. So now, can you see now when we use Pearson's, we have negative, like a very weak negative. But when we use Spearman, we have a positive what I call it, we have positive correlation, but a very weak positive correlation. So Spearman is telling us that as age increases, the mental health scores increases because this is a positive correlation. While Pearson's is telling us that as age increases, the mental health scores decreases. That's what Pearson's is telling us. But this this difference between these two correlation methods you can just try to like read the differences online. So you can read the differences online. You are going to like understand the difference between the two of them. So they are actually different, but sometimes they are going to give you like very closely approximated value. So, and we still have one count that too as well. So yeah.
Sorry, Mr. Daniel, sorry to interrupt you again. Please, I don't know if the file for the RMD R Lab 4 can be sent, because that's not available on the Google Classroom as well. I don't know where others have gotten it from.
Okay. Does anybody have R Lab 4? Let me see.
It wasn't shared in the classroom, so I don't think anybody has it.
Ooh. I mean, let me try to like where I get it from. Sorry, I need to take a bit of time to look for this stuff. June. Sorry, I'm coming. Okay, let me just put this R Lab 4 in my Google Drive. I can just drop the link over here so anybody can download it, because I'm trying to like look for the folder, but I couldn't. I don't know. I don't see the folder where it is.
There's a folder under the comparing. Let me see whether I can get it.
Okay. Comparing means right.
Yes, if you go to, let me see how I downloaded it.
Yeah, I think I'm able to see it. Yeah, thank you very much.
Unit 4, yeah.
Yeah, thank you very much. Thank you very much. How do I get these? Yep. So I just paste a link, so I hope it works.
I have posted another one in the Google Classroom.
Thank you very much. Thank you very much. So you have two ways. You can just download from the Google Classroom.
Okay, can I ask a question, sir?
Okay, yeah, go on.
Okay, so what you just did is when you are comparing only two variables. So in situation where you have, for example, age, and probably you have collected different types of hormones, and you want to do a correlation between age and probably 4 or 5 hormones that you have the data. How do you run that? Because the example just give us is just two variables.
Okay, you mean like you have like age, hormone 1 in a variable, hormone 2 in a variable, hormone 3 in a variable, right?
Yes.
Okay, yeah. Well, there is, how will I put it? Yeah, there is a way to like do that. Yeah, but what happened is that maybe you might need to like how will I put it? You might need to like use this kind of color combination to like, there is a way you can actually do that. Yeah, so you are going to plot, let me say, you are going to plot the age against the hormone, but you are going to like use like a color code, so like differentiate hormone 1 from 2, from 3, from 4. So as you see the points, you are going to see the colors. It's going to tell you how the relationship goes. I don't know if you get what I'm saying.
Not really. Okay. I'm trying to I'm not gotten it like that.
I'm coming. Let me see if we have a perfect example right here. Okay. Okay. Okay, I'm going to come back to that. I'm going to come back to that. So do we all have lab 4 right now?
Yes.
I do.
Okay.
Yes, I do.
Okay. So like this tells like the difference between like what do you call it? This, so you can see that there is difference between the spearman and the persons. So you should know the one you are reporting. So but if you use like Corel.test and you pass this same argument into it, yeah. So yeah, so you are going to have like your test statistics for spearman, right? This is your what I call it, this is your R correlation, this is your this is your correlation value, and it's going to give you like a p-value, a kind of p-value and test statistics to tell you if this relationship between them is significant. If you use called COR.test, so it's going to tell you if the relationship is significant actually. So let's change this to spearman. In this case of spearman, this relationship is not significant actually. There is relationship, but it's not significant. Let's see these two as well. Yeah. So there is relationship between them, negative relationship, but also is not significant. So you can check like looking at your p-value, seeing what happens. So yeah. So that's that. So whenever you have, what are they calling? You have like more than three variables, right? More than two variables, right? Let's try something. Okay. So you tend to like use correlation matrix actually. So let's say if you want to like do this 1, 2, 3, 4, these first four observation, right? So I'm going to use like a subset. I'm coming. What was the RDS subset 1 to 4? So we are going to have like a kind of correlation matrix. So we are going to have correlation matrix. So you can now start comparing between mental health score and age. You go again, mental health score and mental health score. You know, when you are correlating X on X, you are going to get one perfect relationship. Mental health score and job satisfaction, mental health score and workload. Like, so you can see the distribution of how the correlation behave among the four observations. So now for someone asked, if you want to like okay, now maybe you have like let me just say three observations, three variables, and you want to like plot three variables. So now if you plot this on the x-axis, you can plot this on the y-axis, and okay, if you plot this on the x-axis, there is a way we like you change this. You have to like, you can check this data from like a wider range. This is in the wider format now to a longer format. I don't want to go through that because I might want to confuse. Like, let's just try that actually. RDS incoming percent pivots. We need library. Is it the PR? That's all. Is it in this package? I think it's library tie device actually. Tie device, yep. Pivot longer. What's the data? 1, 2, 3, and 4. So 3_4. Name. Let's be name. And values into yeah, okay. What I've just done now is that if you look at these two variables, right? I'm coming 3 and 4. Okay, these two variables, right? What I've just done is that I want to check, like, I just like change them from like a wider range into a longer range. We combined, I create like a column to like have these two attributes against their values. So you see the first two observations will be 10, 10, 44, while the second will be like job satisfaction, workload, 9, this 940, like coming. Let's go back. Can you see 10, 44, 940? So like that. So now you can now use this to like plot your ggplot2 AEX. You have your x variable is what? Age, right? And your y variable will be values. Your y equals values. So x is this and y is values, right? So what you can do now is like we are trying to like plot a point. So AES, you specify color to equals to like name. Let's see, name of the variable. Yep. So can you see? So now this can, because what we do is that we plot age against the value, because we change it from like a two observations, like to be in two variables, to be like in one format variables against their attributes. if the associated value is like job satisfaction or workload. Then we now plot the x-axis, that's the age, against the values. Then we like color it by what I call it by the name of the observation and by the name of the variables. So from here you can see that this is the correlation between this, and this is the correlation between the value, like the what I call it workload and age. So sort of kind of that can give you some big information when you have like two or multiple when you have like more than two values, actually more than two variables actually. So
Please, could you explain it again? Sorry, Daniel. The pivots longer query.
so
What's that 3 to 4?
yeah, now what happened is that I want to find a way to like convert these two, like, okay, this is 1, this 2, this 3, and this 4. So now the question is asking that if I want to check like relationship between, maybe plot relationship between 3 variables, like to see the relationship between 3 variables actually.
Okay.
So now, I have these 2 observations. I'm taking this as my x, and I have these 2 observations to like take y to be on the y-axis. So what I need to do is that I want to like there is no way I can plot this like plot this in that kind of plot. So I need to find a way to like combine these 2 values, like their values to be in a variable, and their attributes should be in another variables.
Okay.
So that was why we use like pivot longer.
So that 3 to 4 is naming the columns that's
exactly
okay.
Yeah. So this is the third and the fourth.
And the fourth column. Okay.
Combine the third and the fourth into name called name and into values called values. So their value we take column name to be values, and their attributes like their names we take name. Then I just like, do you get? I just like plot the plot directly. I can save this into a value, like I can save this into another variable name, then come and plot this.
Yeah, so can you do that so we can see how the transposing works? Because I'm trying to visualize it, but it's not clicking.
Okay. I showed you the transposing, yeah, kind of. So once you come to the very end of this, can you see name?
Okay.
Values.
Okay.
Yeah. So
yeah.
Yeah.
Thank you.
So I just have to just share that because of the question he asked, actually. So that is that. Okay. So now we have another example here using the same resident doctors. So we want to check the age between we want to check the relationship between hours worked and the mental health score. So you want to like, you might be interested in plotting, having a point plot, which this is this, and you can see that maybe you can see the way the points are. From the point, you can easily see if there is relationship between mental health score and the hours worked. So if you check the correlation coefficient, we are going to see negative 0.24. So this is like a very weak relationship between the mental health score and the hours worked. So I think we are fine with correlation, right? Is there any question on correlation?
Not from my end.
Okay. So we need to move to regression. Regression. The difference between correlation and regression is that correlation tells us the relationship between two variables, right? While regression tells us what extents, like, okay, now when I say that the correlation between mental health score and hours worked is there's negative correlation between them. It does not tell us at what rate does hours worked change the mental health score, or how much rate does mental health score change the hours worked. It doesn't tell us, but we might want to be very interested in like knowing like the magnitude of change, the magnitude of relationship. That's why regression, that's how the regression comes in. It will just tell you that there's a relationship. Okay, if you tell me there's a relationship, to what extent is that relationship? So now we have two ways of doing our regression, you know, we have like two, what are they calling? We have to like two functions that you can use for your like simple linear regression or even multiple linear regression. We have the GLM and the LM. The LM is linear models, while the GLM is generalized linear model, like full meaning, just you don't really need that. So now, so let's say you are interested in assessing whether there is a relationship between the resident doctor mental health or mental health and the number of hours work per week. So now we want to like create a model that as the resident, like we want to like know, I want to know the behavior, observational behavior of the mental health of the resident doctor, right? So now we have our Y variable to be the mental health, right? And the X variable to be the hours worked, because we want to use the hours worked to predict the mental health, like the mental health score. So we are going to know, probably we reduce the number of hours work for them if like the number of, if we notice that there is the number of hours worked really affects, like increase their mental health score, all those kind of stuff like that. It depends on the kind of inference you want to make in this sense. So it can take formula in the LM model. So once you take the LM model, the target variables, you specify the target variable, which is your dependent variable. It is known as, it's popularly known as Y variable. Yeah, but Y variable. Then you tie it to your predictors, to your predicting variables, your predictors. Then you specify data source. This is first method. And the second method, you pass GLM, like you use GLM function, your target variable. You tie it with the predictors. You specify the data. If you are using the GLM, you have to use like it takes an argument called family. So this family, this is Gaussian, like they call Gaussian, is normal. We assume that our data are from normal distribution data. So once we use this is it Gaussian? Yeah, Gaussian, we specify Gaussian and the link to the identity. This Gaussian means that our data come from like a normally distributed data. So that's how. So let's try the first approach. So we are interested in like checking the mental health score. We want to like predict the mental health score based on the hours worked from the resident doctor. So we pass using the first approach. You see the what I call the target variable, which is mental health score. Yeah, we tie it to like the predictor, which is hours worked. Then we specify our data. So once we run this line, that's model one. You now you use summary model one to like summarize the model. So once summarize the model, now I'm going to interpret this one. So subsequent one, I won't be the one to interpret it. I will just ask someone to come and please interpret it for us. So now this is the summary from the regression, from the model. This is summary from the model. So we have some key important things we want to summarize. So now this is the intercept. This is the intercept. What this intercept interprets is that whenever hours worked is 0, on average, the mental health score of the resident doctor is 26.35. On average, whenever these hours worked is 0, whenever your predictor value is 0, what did the intercept like interpret? Whenever your predictor is 0, the target variables takes an average value of this. Like on average, takes this value, like it takes that value on average. So whenever, how to interpret is that whenever hours worked is 0, the mental health score of the resident doctor on average is 26.35. Then you put maybe the measurement is 0% or whatever, so like that. So that's how it works. So now for this, and you can see the associated p-value. This is the p-value. This is the estimate. This is the estimate. This is the estimate. This is the standard error. This is the test statistics, and this is the p-value. But what you have to be more concerned about is this estimate and this p-value. So the p-value is lesser than 0.05. Like, so this is very, very significant actually. But most of the time we don't really interpret the p-value for like the intercept, because we are not really interested. Most of the time we are not really interested in the intercept. I might be wrong, depending on what you are doing, but in my own case, most of the time I've never like talked about the intercept. I would just say on average, whenever the predictors is 0, this is what we have on average, and it's tends to be very significant. That's all, and I move on. I'm not really making any inference concerning the intercept. But when it comes to like the predictors, so now, how do you interpret this? You said for every hours of work increase, for 1 unit hours of work increase will lead to reduction of mental health score by 0.37. That is 1 unit increase, that is 1 hour, not 1 unit. Let's just say 1 hour increase in the hours worked will lead to like 0.37 reduction in the mental health score. So, and this is the associated p-value, which is very, very significant. It's very, very significant. That is, there is significant relationship between the hours worked and the mental health score. So that's that. One of the easiest way to know if your variable is significant is that when you look at this, you see these 3 stars, you see these 2 stars, you see this 1 star. This shows that it is very, very significant whenever you see 3 stars. Because if it's significant at 0.0001, it will be significant at 0.05. So that's what this stars means. When you have like 2 stars, you know it's significant at 0.001. Once you has 1 star, it's going at 0.01. So that's how it works. So, but you can just ideally use your eye to know, just compare and see where it's significant. So we have the multiple R square. So multiple R square tells you the variation in your target variable, that is in mental health score, that can be explained by hours of work. So if you convert this to percent, if you convert this to percent, I'm coming 0.76 times 100. If you convert, you are going to have 4.17. So that is, there is 4.17% variation in mental health score that can be explained by hours worked. That's what this tells us. That's what it tells us. But sometimes you can see that this variation is very small. So we need to like add. This is telling us that we need to like, there are some variables that we have not considered, because to have like a very good model, you might have like R square of like, let me just say 70 above. I'm just saying 70 above. Yeah, that shows you that, oh no, this your predictors explain more about your predictor explain more about your target variables. But now this is telling us that we need to add more variables. There are some variables that we did not consider that affect the mental health scores, but they are not considered in this model. So now we have the F statistics. What the F statistics does is that the F statistics is different from these T statistics. This T statistics is like a marginal test. It just tests like it takes the effect of hours worked on mental health score. But this F statistics talks, if you have like multiple variables in this, multiple predictors variable, let me say you have another predictor variable. This in general, this F statistics talks about the all predictors, their contribution to the models. So is like, does the data like fit the models? So as you can see, this is significantly lower than 0.05. So this data fits, like suits this model. So it's very significant. That is, at least like this tells you that at least all the predictors variable, at least they are not 0, that their coefficient are not 0. So I don't know, is there any question? Is there anything you want me to like talk about again? Because this might be the only time I'm going to interpret this. I'm going to like just call someone, ask someone to volunteer to like interpret for us henceforth. So is there any question before we move on?
Yes, please. Can you repeat the significance of the F statistic, what it means? I missed what you said.
Okay, now this F statistics talks about the general contribution of the models. You know, I know you've done the main class for this regression. You know, we have this is assumed to be beta naught, right? This is assumed to be beta 1, right? Beta 2, beta 3. So when you have like, let me say when you have like two dependent variable now, like two independent variable, you have your beta naught, beta 1, and beta 2. So we now want to check this F statistics tells you that the contribution of this and the predictors is not 0. Like at least one of the estimates of the predictors is not 0. It's telling you like the general significance of the model. You can say maybe the model you fit suits the data or it does not suit the data. So the hypothesis is always like the hypothesis is always like all the betas, like all the beta 1, beta 2, beta 3, beta 4 equals to 0. That is all your estimate aside this beta naught. Even if you have like multiple variables, all their betas equals to 0. And the alternative tells you that at least one of the betas is significantly different from 0. So if this p-value is lesser than 0.05 now, you know, you reject the null hypothesis. It's telling you that this coefficient, all these coefficients in your predictors, at least one of them is significantly not 0. That's what it tells. And that is telling you like the overall contribution of the model of the betas to the model, that does the models fit the data or not. Or so I don't know. That answer your question.
Thank you.
Yeah, okay.
Another question.
Okay.
Specifically where you have the significance codes, does that mean like for the house worked, given that it has the 2 dots, it is within the 90% confidence interval? If you can repeat how you explained that, yeah.
Okay. So if you compare this to your to 0.05, you notice that this is like way more lesser than 0.05. So what it does that it tells us that there is actually relationship, the relationship between hours worked and mental health score is very, very significant. That is the relationship, there is the relationship between mental health, how will I put it? I'm coming home. The hours work, there is significance effect. There is significance effect. I'm coming. How do I want to put it?
Hours worked influences
okay.
the mental health
exactly.
status,
Yeah, exactly. That hours work has effect on the mental health score. Thank you for that. Yeah, hours worked has significant effects on the mental health score. So do you get like that?
Yeah, it's clear now.
And what is the effect? This is the effect. For 1 hours increase in hours worked, leads to like 0.03 reduction in the mental health score. So I almost struggle with that. Sorry. So what you need to pay attention to whenever you're like you're like interpreting your regression, you have to pay attention to the estimates. So this is the estimate. You have to pay attention to the standard error. Yeah, this is standard error because ideally this standard error is like the formation of your is the formation of your confidence interval. You can use kind of standard error to know like where maybe the range at which each estimate lies. So the p-value and the r-squares. So we've talked about the p-value, we've talked about the r-squares and the estimates as well. So how do we implement the second method where we use GLM, right? So this is GLM. This is GLM. This is GLM. So once you use GLM function, your target variable, your hours worked, you specify the data, then you specify family because GLM takes a function called an argument called family. So the family equals to like Gaussian, and Gaussian is like telling you that the data come from like a normally distributed data. So you specify your link, which is identity. So once you run this, you are going to have the same thing. Nothing is different. The only thing is just that this is going to tell you like null divergence, reducer divergence, and the AICs. That's what it's just going to tell you. So yeah, but interpretation of the estimates will still be the same thing. Yeah, so that's it. So now we want to, like, after like linear regression, like regression has assumptions. So we want to like validate that the models we've already we want to like evaluate the regression model, and we can assess the goodness of it. The model like we've already built, like it makes sense, it meets the assumptions and all this kind of stuff like that. So you just have to plot the model, pass the model into plot function. So once you plot the model, you can start from the first one. So this plots the residual against the predicted value. So it plots the residual against the predicted value. I think we need to let's just go first, so I can come back and explain this there. Let's just go first. We come back and explain this. So let's go first. So now let's talk about when we have like binary predictors. Yeah, binary predictors. So when you have like binary predictors, binary number is 0 and 1. So let's say, okay, now looking at this, we try to like create a new variable called hours greater than 70. When you want to create a new variable, you specify your data set name, you use the $, hours greater than 70. So this is hours greater than 70. Then you use the pipe operator to say if this is like, if x is like just neglect this. So we are just checking if there is any in the observation. So how to do that is like to use if function. So let's just say if x, this is what we just done. So let me just say RDS equals $, hours worked is greater than 70, right? If it's greater than 70, what did I want out to say? I want out to give to just specify 1. If otherwise, I have to specify 0. So that's what I just want. So this, if greater than 0, if greater than 70, I can say I should say yes. So just like label it yes. And if it's lesser, you should label it no. If you run this, you're going to see yes, no, yes, no, yes, no. If I say 1 and 0, you're going to have 1 0 0 0 0. So that's just going to like convert them into binary. So let's run this line of code. So this is when we use the continuous method, right? When we use the continuous method, so the continuous value. So now let's use the binary, right? So once we use the binary, so we have this value, we have this our intercept, right? This is our intercept, which shows that whenever okay, we said when we were trying to code, we said if the hours work is greater than 70, it should be 1. When it's lesser than 70, that is, it should be 0, right? So you are going to compare your estimates, this one, you are going to compare it with a reference value. So now to compare, to like talk about the intercepts, we said whenever this variable, this predictor is 0, it gives this mental health score on average, right? So this shows that whenever someone works hours, when someone the hours worked is lesser than 70, is lesser than 70 because this is greater than 70. We are comparing to the what are you calling it, to the baseline? Is it baseline? Base to the reference point of 0, which our 0 is in this case is that any value lesser than any resident doctor that work lesser than 70. So whenever whenever a resident doctor works lesser than 70 hours, their mental health score on average is this. Okay, so now for any hours of work greater than 17 hours, that is any resident doctor that works more hours than 70 hours, maybe 71 hours, like for 1 unit increase in the number of hours worked at the baseline of 70 will lead to 0.9621 reduction in the mental health score. That is, for every hour's work above 70 will lead to this reduction in the mental health score. But if you check the p-value, it is not significant. So this is not significant. It's not significant. So do you have any question regarding that? Is there any question regarding that? Okay. Is there any question?
Excuse me, did you interpret the AIC?
Oh no, I did not interpret the AIC because
Okay.
we're not getting to the stage of like talking about the AIC.
All right.
So we're not getting to the stage of interpreting the AIC. So that's how to like interpret that. So now, we are now moving from when we have like binary variable to like categorical variable. So we want to create another variables in our data that we have to like categorize. We have to like categorize the hours into categories. So once you look at this, just look from here, because this is just like specifying if it's any. So if the hours work is lesser than 40, right? If the hours work is lesser than 40, we give it 1. If the hours work, if else, okay, let me just explain how this works. So let's say if else, how the s, let's call hours worked. Hours worked is lesser than or equals to 40. What did I want you to do? I want you to specify 1, comma. So it takes like, okay, if it's lesser than 40, what did I want you to do? That I want you to specify 1. Okay, if it's not lesser than 40, what do you want me to do again? So because we want to like put them into like more than 2 categories, we have to still specify if x, that is, if it's not lesser than 40, that is, if it's greater than 40, I want you to still like check if the hours worked. If the hours worked is lesser than or equals to 60. If it's lesser than or equals to 60, I want you to specify 2. Okay, what if it's not lesser than or equals to 40? It's not lesser than or equals to 60. What do you want me to do again? So because we still have like another category, we still create another category. If else, sorry, not this if else, how the s, hours worked is lesser than or equals to 80. I want to specify 3. So if it's not lesser than or equals to 80, it's not lesser than or equals to 30, it's not lesser than or equals to 40, maybe it's greater than 80. What do you want me to do? I want you to specify 4. So this is all what we've written here. But why we were using dot as a reference is that because we've already piped this RDS, we piped it. It's called pipe operator. That is, if you say this now, if you pipe this now, this function, loading this function, we take reference from this baseline. Loading this function, we take reference from here and from here. Loading this function, it's not loading this function. Running this line of code, we take reference from here, here, and here. Running this line of code, we take reference from here, here, and here, and make a reference to the data. So that's the difference between what was written up here and what is down here. That's the only difference. That's the only difference. Nothing really special. So once you run this, we create another hours called category, right? And we create another one called H categorical X. So you can see in this context, let me go back to this one. In this context, now what we did is that we, instead of making this to be like a numerical 1, 2, 3, 4, we try to like say, oh, if it's lesser than 40, I want you to attribute lesser than or equals to 40 hours. If it's like lesser than 40, lesser than 60, but greater than 40, that should be between 41 and 60, right? So we give 41 to 60 hours. So if it's greater than 60 but lesser than 80, that's between 61 to 80 hours. And if it's greater than 80, what do you want me to do? Is greater than 80, is not lesser than 80, is not lesser than 60, is not lesser than 40. Then I want you to give 81 plus hours. So it's going to like write that into a new variable. So it's going to write that into a new variable. Yeah. So once we run that, so now if you come here now, because our H category like is in numerical form, once you run this model, we are going to see this is what it's going to give you. Yeah, we want to like use categorical predictors, right? This is what it's going to give you. R will not automatically process that this is categorical. When we were saying let it take 1, let it take 2, it's going to like work with the numerical variables, which you have to be very careful. You have to be very careful when you're using categorical variables. So now what we just have to do is that we have to come the other variable that we were specifying. If it's this, let it be this. The second one, I'm coming, let me show that this variable, we write it into a hours category, cat X, right? So you come here and wrap it up with as factors. So what you are telling R is that I want you to treat this variable as factor variable. That's what you are telling R. I want you to treat this variable as factor variable. I want you to treat it as factor variable. So still same formula, same thing, nothing changes, just only that one. Like you have the categorical predictors and you are treating it as factor variables. So once you run this, you are going to have the intercept. You are going to have your B1 to be hours worked for people from between 41 to 60. Hours work for people working from 61 to 80 hours, and hours work for 80 plus. Can someone just omit and try to like interpret this for us? Thank you. Anybody?
I can try. It appears to be showing that based on the significance level of 0.05, there is no difference between the 3 different categories of hours worked.
Okay. Before going to the significance, can we try to like estimate the like interpret the estimate together? So let's see how it goes.
Okay, so looking at the estimate, for the category 41 to 60 hours, it suggests that there's a small positive correlation of 0.34. For the 61 to 80 hours, 0.59. But for the category 81 plus hours, a negative effect or estimate of 0.16. Sorry, 1.7 or 1.68.
Thank you very much. Thank you very much. Yeah, that's just like the idea of everything. But in this context, you are like trying to like compare those values to the reference points of people that work lesser than 40 hours, right?
Mm-hmm.
So now we see what we have to first interpret in this context is that if for any hours, like if like a resident doctor does not work, it does not work like work lesser than or equals to 40. for every resident doctor that work lesser than or equals to 40, they work less than exactly 40 or lesser than 40, their mental health scores is 23.92. So for every resident doctor that works between 41 hours to 60 hours, right? Their mental score will increase by 0.472. For every resident doctor that work 41 to 60 hours, the mental score will increase by this amount. So now, for every resident doctor that work 61 to 80 hours, the mental health score will increase by this percent. So now, for every resident doctor that works 81 hours plus, if you work 81 hours plus, their mental health score will reduce by this compared to those who work 40 hours. So this will increase by this compared to those who work 40 hours. This will increase by this compared to those who work 40 hours. For anybody that works between 41 to 60 hours, their mental health score will increase by this percent, by this amount, compared to like those who work 40 hours. So if you add this plus this together, it's greater than this. If you add this plus this together, it's greater than this. If you minus this from this, you see that these people work, their mental health score is lower than every other one in the group. So do you understand now?
I personally understand, but what is the logic behind that? How comes from 80 plus the score goes down? I thought it should even go higher. A higher mental score doesn't mean that you're getting worse.
Yeah. So yeah, my own question, my own work over here is to like make conclusions based on the data. So the question now to now start asking why. Like you have to start asking why and looking at maybe more factors that might contribute to like maybe people working. When you say people working 80 plus hour and having like a lower mental score, there might be other factors that we might not have considered. That's why you have to like consider all those factors. But now this is the first like step to that, like trying to like answer a question on why. This just telling you what happens. Then you can now start asking yourself why. Why is this? Why is this? Why is this? Why is this? So, and you can also check the p-values. You can see that they are not significant. So the chances of someone working between 41 hours to 60 hours will having increased in their mental health score is not significant. This also is not significant. This also is not significant. It's not significant. So that's how to like interpret that with respect to like the base reference point, which is lesser than or equals to 40 hours. So I think we should stop here because we have how many minutes? We have 3 minutes left. Oh, 2 minutes. So we can just like I can take questions if you have any questions. Yeah. So I think next week we are going to continue here. Ideally, the aim of like the scope of this class is that we finish this lab 4 today. But we are just due to like some data problems we are having, we could not like move as fast as possible. And we have been having like, let me say, we have been having like some few slides to like finish, like some few code to like finish in our previous classes from the day one. So that was why we are still trying to like lag behind. So do you have any question before we call it a day?
I just wanted you to still repeat on the concept of piping, the pipe operator.
Oh, okay. Coming. So how would I explain? Okay, now let me try to create a new file. Okay. So what pipe operator does is that it helps you to like chain your line of code together and give you a particular output. Like it processes everything at once. So we have our RDS data, right? Let's see the names in RDS data. So to know what I have to like do that outside the okay, names. Okay. So we have age worked, we have mental health score, right? Okay, now let's say we want to plot age, and mental health score. No, okay, no, don't let me do it like that. Let's do this. No, let's say we want to select the the first 4 variables in the data set. You can use this 1 to 4, right? It's going to select the first 4 variables, right? So now, instead of using this, I might want to like pipe and say this. No, this. Don't let me go that way. Sorry, don't let me go that way. I'm looking for like going the most simplest route, because so that you can understand the logic behind this pipe. Okay, now let me say I want to plot age and mental health score, right? I can just come and say ggplot. If I'm using ggplot, right? AES, okay, RDS, AES equals what? Equals age, and my Y variable equals mental health score plus geom point. So I'm going to have my plot over here. This is my plot, right? That's not what we are interested in. So now, can you see the way I plot this? Because ggplot takes data. This function here is data equals this. It takes x equals this, and it takes y equals this, right? Okay, now if I want to use pipe operator, RDS, so automatically I have already chained this data name, like this my data set name. I've already chained it to any function I want to write. So what I just need to like say is ggplot AES. I will just go to AES instead of specifying data again, because I've already piped this data line into the length line. What this is going to do is that this line, to run this line is going to like take reference from this previous line. So when I say AES equals age, mental score plus geom point. So this geom point is going to take reference from this and this. Ideally, I should specify my data here, but I will not specify my data. Why I'm not going to specify my data is that because I've already piped this data name, I've piped it into the length line. So it reads backward. It's going to like, this is the data actually. So any function anything I'm doing here, making reference to the data. I don't need to make reference to the data again because I've already piped this data into it. So automatically it's going to like see anything I'm talking, any reference I'm making towards data, it's going to read it through. So it's going to read it through. I don't know if that understand how pipe works. It's just like you don't have to start repeating, start saying the RDS $. No, you don't have to do that. You just have to just make reference to like the variable names. It's going to read backward to the main data set and perform any function you want to do.
Yes, that is perfect. Thank you.
Okay, yeah. So let's call it a day. So see you next week. So in case you have any question, you can just put it in the Google Classroom. So the StatsClinic team will be there to assist you with any question. Thanks for attending this section.